In the beginning, there was nothing, and then, as popular imagination would have it, that nothing exploded into everything we see today. But this conception of cosmic origins represents just one of countless misconceptions that have shaped humanity's understanding of the universe. These myths, some ancient and others surprisingly modern, persist in textbooks, conversations, and even scientific discussions. They form a tapestry of misunderstanding that obscures the far more extraordinary reality of how our cosmos actually functions. What follows is an exploration of the universe's most persistent falsehoods, arranged from the obvious to the profound, from the simple to the mind-bending paradoxes that challenge the very foundations of our perception. The illuminated shadows. Consider Earth's closest celestial companion, the moon, hanging in our night sky with what appears to be two distinct faces. For generations, people have spoken of the moon's dark side, an eternal realm of shadow where sunlight never penetrates. This notion has captured imaginations, inspiring science fiction narratives, and perpetuating the idea of a permanently shrouded hemisphere. The reality, however, tells a different story entirely. The moon does maintain a tidal lock with Earth, meaning the same face always points toward our planet. This gravitational embrace ensures that from Earth's surface, we observe only one lunar hemisphere throughout our entire lives. But tidal locking affects orientation, not illumination. As the moon completes its orbit around Earth, sunlight bathes every square kilometer of its surface in a predictable pattern. During what we observe as a new moon from Earth, the far side actually experiences full illumination. The lunar day stretches across approximately 14 Earth days of continuous sunlight, followed by an equally long night. No portion of the moon exists in perpetual darkness. No shadowed craters remain forever frozen in time. The confusion stems from conflating the far side, which we cannot see from Earth, with a dark side, which simply does not exist. Every region of the moon experiences the same cycles of day and night, each lasting roughly 2 of our weeks. This brings us to another temporal misconception embedded in our very language. We speak of months as if they were arbitrary divisions of the year, noting how February contains fewer days than August. Some imagine the moon itself somehow accelerating and decelerating in its orbit to accommodate our calendar. The truth reveals a more elegant clockwork mechanism. A lunar month, the time required for the moon to complete one full orbit around Earth, takes a constant 27.3 days. This period remains unchanging, unaffected by the varying lengths of our calendar months. The calendar months we use derive from ancient Roman traditions, modified repeatedly through history for political and practical reasons. February's brevity owes nothing to celestial mechanics, and everything to Julius Caesar and subsequent reformers. The moon maintains its steady orbital pace, indifferent to human timekeeping conventions. When we speak of a month, we invoke two separate concepts: the lunar month defined by celestial motion, and the calendar month defined by human convention. They coincide only imperfectly, creating the need for complex systems to keep our solar-based year synchronized with lunar observations. The limits of human perception. From space, Earth presents a stunning vista of blue oceans, green continents, and white clouds. Astronauts have described the profound emotional impact of seeing our planet from this vantage point, an experience that fundamentally alters one's perspective on human existence. Against this backdrop, many believe one human structure stands visible to orbiting observers: the Great Wall of China. This claim has appeared in textbooks, tourist guides, and countless retellings. It suggests a monument so massive, so significant, that it bridges the gap between human scale and cosmic perspective. The mathematics, however, tell a different story. The Great Wall stretches for thousands of kilometers across northern China, an undeniably impressive feat of engineering and human persistence, but its width averages a mere 7 meters. The International Space Station orbits at approximately 400 kilometers above Earth's surface. From this distance, spotting a 7-meter-wide structure becomes geometrically impossible for the unaided human eye. Consider the equivalent perspective, attempting to identify a spider's single silk thread from 50 meters away. Even with binoculars, such a task exceeds human visual capabilities. The atmospheric distortion, the sheer distance, and the limits of optical resolution combine to render the Great Wall invisible to astronauts. What they can see are cities, which glow brilliantly at night, and large-scale geographical features, like river deltas and mountain ranges. The Great Wall, despite its historical and cultural significance, remains too narrow to register against the vast panorama of Earth's surface. Aboard that same space station, astronauts float effortlessly, performing acrobatic maneuvers impossible on Earth's surface. Videos show them tumbling, drifting, and moving objects that would require tremendous effort in terrestrial environments. This apparent defiance of gravity has led many to believe that gravity itself ceases to exist at orbital altitudes, that astronauts have somehow escaped Earth's gravitational influence. The reality proves far more fascinating. Gravity at the space station's altitude remains approximately 90% as strong as the force we experience standing on Earth's surface. If gravity truly disappeared at 400 kilometers, the Moon, orbiting at 384,000 kilometers, would long ago have drifted into interstellar space. The station's inhabitants float not because gravity has vanished, but because they exist in a state of continuous freefall. The station and everything inside it, including the astronauts, plummet toward Earth constantly. However, the station also possesses tremendous orbital velocity, moving sideways so quickly that as it falls toward Earth, the planet's curved surface falls away beneath it at the same rate. This perfect balance creates what scientists call microgravity, not zero gravity. The astronauts fall endlessly, missing Earth perpetually, their sideways motion perfectly offsetting their downward acceleration. If you could somehow position yourself in the vast emptiness between galaxies, millions of light years from the nearest significant mass, you would still experience gravitational pull. It would be infinitesimally weak, perhaps immeasurable with current technology, but it would exist. Gravity extends infinitely through space, weakening with distance but never truly reaching zero. The concept of zero gravity represents an idealized abstraction, useful for certain calculations, but never achieved in physical reality. The fragility of human biology. Science fiction films have burned particular images into collective consciousness. Astronauts exposed to vacuum, their bodies swelling and rupturing in spectacular explosions, blood boiling instantly in their veins. These dramatic depictions serve narrative purposes, but bear little resemblance to the actual effects of vacuum exposure on human tissue. The reality, while certainly fatal, unfolds with less explosive drama. In 1965, NASA conducted a series of experiments testing the limits of spacesuit design. During one such test, a suit failure exposed a test subject to near vacuum conditions. The subject lost consciousness after approximately 14 seconds. Later reports documented his final conscious moments. He recalled feeling the saliva on his tongue beginning to boil as the reduced pressure lowered water's boiling point to body temperature. Rescue came quickly, and the subject recovered without permanent injury. This incident, while terrifying, revealed the actual progression of vacuum exposure. Without air pressure, the gases dissolved in bodily fluids begin to form bubbles, a condition similar to decompression sickness experienced by divers. The water on exposed surfaces, including eyes, mouth, and skin, begins to evaporate rapidly. The expanded gas in the lungs, if held forcefully closed, could cause damage. But the body does not explode. Skin possesses sufficient tensile strength to contain internal pressure. The heart continues beating briefly, though without oxygen, brain function ceases within seconds. Death would follow within 1 to 2 minutes, but from asphyxiation and pressure-related injuries, not explosive decompression. The human body, remarkable in its resilience, can withstand brief vacuum exposure if repressurized quickly enough. Longer exposures prove fatal, but the process resembles drowning more than exploding. Symbols on a distant world. Between 1969 and 1972, American astronauts planted 6 flags on the lunar surface. These symbols, carried across 400,000 kilometers and placed with ceremony, represented not just national pride, but human achievement itself. Images of astronauts standing beside these flags became iconic, among the most recognizable photographs in human history. Many assume these flags still stand today, frozen monuments on an unchanging world. The reality proves more nuanced. In 2016, NASA's Lunar Reconnaissance Orbiter captured images showing that at least 5 of the 6 flags remain upright, their shadows visible in the lunar regolith. However, the flags themselves have likely undergone significant transformation. For over 50 years, these nylon flags have endured unfiltered solar radiation, with no atmosphere to absorb or scatter the sun's most damaging wavelengths. Ultraviolet light breaks down molecular bonds in fabric and dyes. Scientists estimate that the flags have been bleached white, their colors destroyed by decades of constant radiation. The Chinese flag planted by the Chang'e 5 mission in 2020, by contrast, remains relatively fresh, its colors still vibrant. But both Chinese and American flags share a common engineering feature, a horizontal support bar along the top edge. The moon possesses no atmosphere, and therefore no wind. A conventional flag would simply hang limp against its pole. The support bar creates the appearance of a flag caught in breeze, a purely aesthetic choice that creates a more visually striking scene. One American flag from Apollo 11 toppled when the lunar module's engines ignited for the return journey. The others remain standing, bleached monuments to an earlier era of space exploration. The nature of starlight. On a clear night far from city lights, the stars appear to twinkle and shimmer, their light dancing across the darkness. This twinkling quality has inspired poets and musicians, becoming synonymous with the romantic quality of starlight itself. It seems natural to assume that stars themselves flicker and pulse, that their light output varies moment to moment. The reality reflects a quirk of observation rather than stellar behavior. Stars, massive spheres of fusing hydrogen many millions of kilometers in diameter, do not pulsate every second. Such rapid oscillations would require inconceivable energy variations. Instead, stars emit steady, continuous light across millions and billions of years. The twinkling we observe occurs entirely within Earth's atmosphere. Air masses of different temperatures and densities refract light slightly differently. As these air masses move and mix, they create constantly shifting lenses that bend starlight along subtly different paths. From our perspective on the ground, this appears as twinkling. Astronomers refer to this phenomenon as atmospheric seeing, and it represents one of the primary challenges of ground-based telescope observation. On the moon, which lacks any atmosphere, stars appear as steady, unwavering points of light. They do not twinkle at all. This difference reveals the atmospheric nature of the effect. Professional observatories are built on mountaintops and in desert regions specifically to minimize atmospheric interference. They seek locations where the air remains stable and clear, reducing the seeing effects that blur celestial observations. The development of adaptive optics, systems that rapidly adjust telescope mirrors to compensate for atmospheric distortion, represents another approach to overcoming this challenge. Space-based telescopes like Hubble bypass the problem entirely, observing from above the atmosphere's distorting influence. The rhythm of seasons. As Earth orbits the Sun, the distance between the two bodies varies significantly. Our planet follows an elliptical path, bringing it closer to the Sun at some points and farther away at others. This variation amounts to approximately 5 million kilometers between the nearest and farthest points. Given this substantial difference, it seems logical that seasons result from these distance changes. When Earth moves closer to the Sun, we might expect warmer temperatures. When it moves farther away, we would anticipate cooler conditions. This explanation, while intuitive, fails immediately when confronted with a simple observation. Seasons occur at opposite times in different hemispheres. When North America experiences summer, Australia endures winter. When Europe basks in July warmth, Argentina shivers through cold July nights. If distance alone determined temperature, the entire planet would warm and cool in unison. The actual mechanism reveals Earth's axial tilt as the dominant factor. Our planet spins on an axis tilted approximately 23.5 degrees relative to the plane of its solar orbit. This tilt means that during one portion of Earth's orbit, the northern hemisphere leans toward the Sunday sunlight strikes this hemisphere more directly, with rays arriving nearly perpendicular to the surface. Direct sunlight delivers more energy per unit area. Additionally, the sun appears higher in the sky and remains above the horizon for more hours each day. This combination of direct illumination and longer days creates summer. 6 months later, when Earth reaches the opposite side of its orbit, the same tilt causes the northern hemisphere to lean away from the Sunday. Sunlight arrives at oblique angles, spreading the same amount of energy across larger areas. The sun appears lower in the sky and remains visible for fewer hours. Winter conditions result. The southern hemisphere experiences the opposite pattern during the same periods. The distance variation does have a minor effect, but it's overwhelmed by the tilt's influence. Interestingly, Earth actually reaches its closest point to the sun in early January, during northern hemisphere winter, demonstrating that distance plays a secondary role at best. Visitors from the void. When meteorites strike Earth, they arrive with tremendous velocity, having plunged through the atmosphere at speeds that can exceed tens of thousands of kilometers per hour. The friction generated by this passage through increasingly dense air creates spectacular light shows, the shooting stars that have inspired wishes and wonder throughout human history. Given the enormous energies involved, and the brilliant fire trails that mark their descent, it seems natural to expect meteorites to arrive at the surface red hot, perhaps even molten. Hollywood reinforces this image, showing impact sites glowing with heat and characters unable to approach recovered meteorites without protective gear. The reality surprises most people. Meteorites typically arrive cold, sometimes even frozen. The fiery atmospheric passage occurs at high altitudes, typically 20 kilometers or more above the surface. At these heights, the meteorite's surface does reach extreme temperatures, hot enough to vaporize rock and create the glowing plasma trail we observe as a shooting star. However, this superheated phase lasts only seconds. As atmospheric drag slows the meteorite to terminal velocity, typically somewhere between 200 and 400 kilometers per hour, the heating ceases. The meteorite then falls the remaining distance as a cold rock, tumbling through kilometers of frigid high-altitude air. This cooling process proves highly efficient. The meteorite's small thermal mass loses heat rapidly to the surrounding air. By the time it impacts the ground, its exterior has cooled to ambient temperature or below. The interior may retain some warmth, but nothing approaching the dangerous temperatures suggested by popular media. Scientists collecting fresh meteorites often find them covered in frost, condensation forming on their cold surfaces in the warmer near-ground air. Some meteorites recovered from Antarctica have remained frozen for thousands of years, their original solar system materials preserved in pristine condition by the cold and dry environment. The dance of shadows. Few astronomical phenomena capture human attention as completely as a solar eclipse. The gradual dimming of daylight, the appearance of stars during what should be day, the sun's corona blazing around the moon's silhouette, all combine to create a primal, awe-inspiring experience. Solar eclipses feel rare because most people experience only one or two in their lifetime, if any. This personal scarcity has led to the perception that eclipses themselves are rare astronomical events. The reality reveals a much more active schedule. Solar eclipses occur somewhere on Earth between 2 and 5 times every year. The moon's orbital geometry and the mechanics of celestial alignment dictate this frequency. The rarity stems not from the events themselves, but from their visibility. Each solar eclipse casts a shadow that races across Earth's surface in a narrow path, typically between 50 and 200 kilometers wide. The shadow moves at supersonic speeds, sweeping across thousands of kilometers in a matter of hours. Most of Earth's surface is ocean, and most of the land areas are sparsely populated. The mathematical probability of any given location experiencing a total solar eclipse averages once every 300 to 400 years. Major cities might wait centuries between direct hits. This explains why eclipse chasers travel globally, pursuing the shadow path wherever it falls. They understand that while eclipses happen frequently on a planetary scale, experiencing one requires being in precisely the right place at exactly the right time. Lunar eclipses, by contrast, are visible from the entire nighttime hemisphere of Earth, making them far more accessible to casual observers. The moon passes through Earth's shadow several times per decade, and anyone on the night side can observe the event. The true color of our star. From childhood, we learn to color the sun yellow or orange. Countless drawings and paintings depict our star in these warm hues. The term yellow dwarf appears in scientific literature, seemingly confirming this characterization. When we glance at the sun during sunrise or sunset, it indeed appears orange or red. This consistent visual experience seems to settle the question definitively. Yet if you could observe the sun from space, beyond Earth's atmospheric interference, you would find it appears white, not yellow. The sun emits light across the entire visible spectrum, from violet through red, in proportions that combine to appear white to human eyes. The yellow and orange colors we associate with the sun result from atmospheric scattering. Earth's atmosphere preferentially scatters shorter wavelengths of light, particularly blue and violet, more than longer wavelengths like red and orange. When sunlight passes through the atmosphere, this scattering removes blue light from the direct beam, redirecting it in all directions and creating our blue sky. The remaining light, depleted of blue wavelengths, appears shifted toward yellow and orange. This effect intensifies when the sun sits low on the horizon, forcing its light to travel through more atmosphere. At sunset and sunrise, the extreme scattering removes even yellow and green wavelengths, leaving predominantly red light to reach our eyes. The dramatic red and orange colors of these times reflect the ultimate extension of the same scattering process that makes the sky blue and the midday sun appear yellow. The designation yellow dwarf for the sun represents something of a historical accident. Early stellar classification systems grouped stars by color and size. The sun, compared to the largest known stars, appeared relatively small, earning it the dwarf designation. The yellow label came from its appearance from Earth. Modern astronomy has moved beyond these terms, recognizing them as somewhat misleading. The sun is neither particularly small, it outmasses 80% of stars in our galaxy, nor truly yellow. It's a G-type main sequence star, a classification based on spectral characteristics rather than subjective color perception. The dramatic red and orange images of the sun seen in scientific photography represent another source of confusion. These images typically isolate specific wavelengths of light, such as the hydrogen alpha emission line, which appears in the red portion of the spectrum. This technique allows astronomers to study particular features of the solar atmosphere, like prominences and filaments. The resulting images are then color-coded to highlight these features. They are not true color representations, but rather diagnostic tools. From up close, without an atmosphere to scatter its light, and without wavelength-specific filters, the sun would appear as a blindingly brilliant white sphere. The demotion of a world. In 2006, the International Astronomical Union made a decision that reverberated through classrooms, planetariums, and popular culture. Pluto was reclassified from a planet to a dwarf planet. The announcement generated widespread controversy and emotional responses. Many assumed Pluto had been demoted due to its small size, that a threshold existed below which worlds could not qualify as planets. This interpretation, while understandable, misses the actual reasoning behind the reclassification. The IAU established 3 criteria for planetary status. First, the object must orbit the Sun rather than another planet. Pluto clearly satisfies this requirement, following an elliptical orbit that takes 248 Earth years to complete. Second, the object must possess sufficient mass for self-gravity to pull it into a roughly spherical shape. Pluto meets this criterion as well, having achieved hydrostatic equilibrium with a diameter of approximately 2,370 kilometers. The third criterion proved Pluto's downfall. A planet must have cleared its orbital neighborhood of other objects. This requirement means that the planet must be gravitationally dominant in its orbital zone, having either incorporated other objects through collision, captured them as satellites, or ejected them through gravitational interactions. Pluto shares its orbital region with thousands of other Kuiper Belt objects, many of comparable size. The orbital zone remains crowded with debris, uncleared by Pluto's gravitational influence. Astronomers quantify this characteristic using the planetary discriminant, a measure comparing an object's mass to the total mass of other bodies sharing its orbital zone. Earth's planetary discriminant exceeds 1,700,000, meaning Earth's mass dominates its orbital region by that factor. Pluto's planetary discriminant barely reaches 0.07. It represents merely one object among many in the Kuiper Belt, unable to gravitationally control its neighborhood. This distinction proves crucial for classification purposes. If Pluto were considered a planet, consistency would require granting planetary status to dozens of similar Kuiper Belt objects. Eris, discovered in 2005, actually exceeds Pluto's mass. Should it be a planet? What about Makemake and Haumea? Where would the line be drawn? The IAU's decision attempted to create a meaningful distinction based on physical processes rather than arbitrary size cutoffs. The term dwarf planet acknowledges Pluto's spherical shape while recognizing its failure to dominate its orbital environment. Size alone does not determine planetary status. Otherwise, Jupiter's moon, Ganymede, which exceeds Mercury in diameter, would qualify as a planet. The controversy surrounding Pluto's reclassification highlights how scientific understanding evolves and how emotional attachments form to familiar classifications, even when those classifications prove inadequate for describing reality. 2 eyes on the cosmos. When the James Webb Space Telescope began returning images in 2022, many descriptions labeled it as Hubble's replacement, or Hubble. But better. This characterization, while convenient, fundamentally misrepresents the relationship between these 2 extraordinary instruments. They do not occupy the same niche, with one simply outperforming the other. Instead, they observe different aspects of the universe using different regions of the electromagnetic spectrum. Hubble primarily operates in visible light, the same wavelengths detected by human eyes, along with some ultraviolet and near-infrared capability. It sees the universe much as our eyes would if we could travel to its location above Earth's atmosphere. Hubble's images showcase stunning visual beauty, the pillars of creation, colliding galaxies, distant nebulae in brilliant color. These observations reveal the universe as it appears in the present, or at least the present as defined by the time light took to reach us. The James Webb Space Telescope operates almost entirely in infrared wavelengths, specifically the mid and near-infrared regions of the spectrum. This different perspective grants it unique capabilities. Infrared light penetrates dust clouds that block visible light completely. Regions of star formation, shrouded in dense molecular clouds, become transparent in infrared observation. Webb can peer into stellar nurseries, observing the birth of stars in detail impossible for Hubble. More significantly, the expansion of the universe itself makes Webb's infrared sensitivity crucial for observing the earliest galaxies. Light from the most distant objects has been stretched by cosmic expansion, shifting it from visible wavelengths into the infrared. These ancient galaxies, formed less than 1 billion years after the Big Bang, appear redshifted beyond what Hubble can easily detect. Webb sees them clearly, looking back through cosmic time to observe the universe's first generations of stars and galaxies. The comparison to airplanes and submarines captures this distinction. Both are vehicles, but they operate in fundamentally different environments. Asking which is better misses the point they serve different purposes. Hubble provides visual light observations of cosmic phenomena, while Webb reveals infrared signatures invisible to human eyes. Together, they offer complementary views, each revealing aspects of the universe the other cannot easily observe. The edges of observable space. The Big Bang occurred approximately 13.8 billion years ago, marking the beginning of cosmic expansion. Light travels at 300,000 kilometers per second, covering 1 light-year of distance in 1 year of time. Given these facts, simple arithmetic suggests the radius of the observable universe should equal 13.8 billion light-years. Light has had 13.8 billion years to travel. Therefore, it should have covered 13.8 billion light-years of space. This reasoning seems airtight, but it ignores a crucial factor: the expansion of space itself. Light traveling through expanding space behaves like someone walking up an escalator that itself moves downward. The walker makes progress, but the escalator's motion complicates the calculation. Space has been expanding throughout the entire period that light has been traveling toward us. The light that left the most distant observable objects 13.8 billion years ago has been journeying toward us ever since. But during that journey, space itself has stretched. The objects that emitted that light have moved farther away due to expansion. Today, those same objects now lie approximately 46 billion light-years distant. This distance defines the radius of the observable universe. The sphere of observable space around Earth spans 93 billion light-years in diameter. Despite the universe being only 13.8 billion years old, this counterintuitive result reflects the non-intuitive nature of cosmic expansion. The observable universe represents the limit of what we can possibly see, defined by the distance light could have traveled since the Big Bang while accounting for expansion. Beyond this horizon lies more universe, but light from those regions has not had time to reach us. As time passes, the observable universe grows larger, revealing previously hidden regions. However, the acceleration of cosmic expansion complicates this picture. Distant objects are moving away from us faster than nearby ones. Beyond a certain distance, objects recede faster than light travels through space. Light leaving these objects toward Earth makes progress, but the space between us and them expands faster than the light can close the gap. We will never see these regions despite their existence. The observable universe, therefore, does not encompass everything that exists, only everything that can possibly be observed given the finite speed of light and the expansion history of the cosmos. The nature of cosmic genesis. Perhaps no aspect of cosmology suffers from more misconceptions than the Big Bang itself. Popular depictions show an explosion, a central point from which matter and energy blast outward into surrounding space. This visualization, while visually compelling, misrepresents the actual model in fundamental ways. The Big Bang was not an explosion in any conventional sense. Explosions involve matter and energy expanding from a high-density region into surrounding lower-density space. They have a center and an edge, a shock wave propagating outward. The Big Bang possessed none of these characteristics. It represents the beginning of space itself, not an explosion within pre-existing space. Approximately 13.8 billion years ago, space was extremely hot and dense, but it was already everywhere. There was no central point, no location where the Big Bang happened. It occurred uniformly throughout all of space simultaneously. Imagine the entire universe filled with infinitely dense points, all expanding at once. Every location was the center, and nowhere was the edge. The expansion itself proceeded at extraordinary rates. During the inflationary epoch, hypothesized to have lasted from approximately 10 to the negative 36 seconds to 10 to the negative 32 seconds after the initial expansion began, space grew exponentially. The scale of the universe increased by a factor of at least 10 to the 26, expanding from smaller than a proton to approximately the size of a galaxy or larger. This expansion rate far exceeded the speed of light, apparently violating Einstein's relativity. However, relativity constrains the motion of objects through space, not the expansion of space itself. No physical law prevents space from expanding at any rate whatsoever. Objects embedded in expanding space maintain their local physics while being carried apart by the growing space between them. The inflationary epoch solved several problems in cosmology, explaining why the universe appears remarkably uniform in all directions, and why its geometry appears flat. After inflation ended, expansion continued at slower rates, governed by the balance between gravitational attraction and cosmic expansion. This expansion continues today, with distant galaxies moving away from us as space grows between us. The common visualizations showing the Big Bang as an explosion from a point actually depict the expansion of our observable universe, not the Big Bang itself. They show the region of space visible to us growing from an extremely small, hot, dense state into the current observable cosmos. This representation has pedagogical value, but should not be mistaken for a complete picture. The actual Big Bang, if it could be visualized, would show infinite space in all directions simultaneously beginning to expand. No animation can adequately capture this concept because our minds naturally think in terms of objects within space, rather than space itself changing. The inescapability of singularities. Black holes represent perhaps the most extreme objects predicted by general relativity. Their gravitational fields grow so intense that space itself curves back on itself, creating a region from which nothing can escape once it passes the event horizon. Light approaching the event horizon bends increasingly steeply, until at the horizon itself, it must travel in directions that lead only inward. This description has led to the widespread belief that nothing, under any circumstances, can escape from a black hole. The statement appears in countless science education materials. However, Stephen Hawking demonstrated in 1974 that black holes actually emit radiation through a quantum mechanical process. This Hawking radiation represents the only known mechanism by which black holes can lose mass and energy. The mechanism involves virtual particle pairs, quantum fluctuations that constantly occur throughout space. Normally, these particle-antiparticle pairs form and immediately annihilate, lasting for such brief periods that they remain virtual rather than real. At the edge of a black hole's event horizon, however, something different can happen. If a virtual pair forms precisely at the horizon, one particle might fall into the black hole while the other escapes. The escaped particle becomes real, having effectively borrowed energy from the black hole's gravitational field to materialize. From an outside observer's perspective, the black hole has emitted a particle. The particle that fell in carries negative energy relative to the outside universe, reducing the black hole's total mass energy. This process proceeds extremely slowly. A black hole with the mass of our Sun would emit Hawking radiation at such a low rate that its temperature would be less than a billionth of a degree above absolute zero. It would take 10 to the 67 years for such a black hole to evaporate completely. This timescale exceeds the current age of the universe by factors so large they defy comprehension. For comparison, multiply the Sun's current lifetime, approximately 5 billion years, by 1 trillion, and you approach roughly 1% of a solar mass black hole's evaporation time. Supermassive black holes, those with millions or billions of solar masses, would persist even longer. They would continue absorbing cosmic microwave background radiation long after Hawking radiation would theoretically cause them to evaporate. Despite these extraordinarily long timescales, Hawking radiation represents a fundamental prediction about black hole behavior. In the unimaginably distant future, in a universe that has expanded into cold darkness, the last black holes will slowly evaporate, their Hawking radiation representing the final significant energy emissions in the cosmos. The statement that nothing can escape black holes must therefore be qualified. Classical matter and light cannot escape once they cross the event horizon, but quantum mechanical processes allow black holes to radiate energy, gradually diminishing their mass until they vanish entirely. The fatigue of photons. Astronomers observe that light from distant galaxies appears shifted toward longer wavelengths, toward the red end of the spectrum. The farther away a galaxy lies, the more its light appears red-shifted. This observation represents one of the key pieces of evidence for cosmic expansion. However, an alternative explanation has occasionally been proposed. Perhaps photons simply lose energy during their journey through space, growing tired and shifting toward longer wavelengths as they travel. This tired light hypothesis appears to explain the observations without requiring space itself to expand. However, it fails to account for numerous other observations and contradicts well-established physics. In general relativity, the wavelength of light depends on the geometry of spacetime through which it travels. As light traverses expanding space, the space between successive wave crests literally stretches. A photon with a certain wavelength emitted in the distant past travels through space that is itself expanding. By the time the photon reaches us, the wavelength has been stretched proportionally to how much space has expanded during its journey. This mechanism perfectly explains why more distant galaxies show greater red shifts. Their light has traveled through more expanding space. The tired light hypothesis, by contrast, would require photons to interact with something during their journey, losing energy through these interactions. No known mechanism could produce the observed effects without also blurring distant images beyond recognition. Additionally, the tired light model cannot explain the time dilation observed in distant supernovae, which appear to evolve more slowly, precisely as predicted by cosmic expansion. Redshift can also result from gravitational effects. Light climbing out of a deep gravitational well loses energy, shifting toward longer wavelengths. This gravitational redshift occurs near massive objects like black holes and neutron stars. Photons emitted near the event horizon of a black hole become severely redshifted by the time they escape to infinity. This effect differs mechanically from cosmological redshift, but produces similar observational signatures. White dwarf stars show measurable gravitational redshift in their spectral lines due to their intense surface gravity. These multiple sources of redshift, cosmological expansion, and gravitational potential changes combine to shape the light we receive from distant cosmic sources. The boundaries of everything. When we contemplate the expanding universe, our minds naturally attempt to visualize this expansion. We imagine the universe as a balloon inflating, with galaxies stuck to its surface like dots moving apart as the balloon grows. This analogy captures certain aspects of expansion, but introduces a misleading implication. If the universe is like a balloon, what is it expanding into? A balloon expands into the surrounding air. If the universe expands, does it expand into some pre-existing space? This question assumes that the universe must be expanding into something, that it must have an edge beyond which lies something else. The actual model contains no such boundary. The universe does not expand into anything. Space itself grows, creating additional distance between distant objects without requiring any external space to expand into. Imagine the universe as an infinite three-dimensional grid. As time progresses, the spacing between grid points increases. From the perspective of any grid point, all other points are moving away, with more distant points receding faster. Yet there is no center and no edge to this expansion. The grid extends infinitely in all directions at all times. This infinite extent means the universe has no boundary, no place where space ends and something else begins. The observable universe, by contrast, does have a boundary, but this boundary exists in our perspective, not in physical space. We can observe only the region from which light has had time to reach us since the Big Bang. This observational limit creates a sphere around us, centered on Earth, extending 46 billion light-years in all directions. But if we could instantly travel to the edge of our observable universe, we would find ourselves in a region looking much like our own, surrounded by galaxies and space in all directions. That location would have its own observable universe, overlapping with ours but extending into regions we cannot see. The concept resembles being in a vast fog. You can see only a certain distance in any direction before the fog blocks your view. But the fog extends beyond your vision, and someone standing at the limit of your sight range would have their own visible region, extending in directions you cannot perceive. The observable universe represents our cosmic horizon, the limit of what can possibly be observed, not the edge of existence. Some cosmological models propose that the universe could be finite but unbounded, possessing no edge despite having finite volume. A two-dimensional analogy helps visualize this. The surface of a sphere has finite area but no edge. Travel in any direction and you'll never reach a boundary, eventually returning to your starting point. A three-dimensional space could curve similarly in 4 dimensions, creating a finite volume with no boundary. Current observations suggest the universe's geometry appears flat, or very nearly flat, but measurements cannot rule out extremely subtle curvature. If the universe curves slightly and positively, it could form a 3-dimensional hypersphere. Travel far enough in one direction, wait long enough, and you might theoretically return to your starting point from the opposite direction. Such a universe would be finite in volume but infinite in the sense that you could never reach an edge. These considerations demonstrate how cosmic expansion challenges our intuitive understanding of space itself. The genesis of reality. Perhaps the most profound question facing cosmology concerns the ultimate origin of everything. How did something arise from nothing? Our everyday experience teaches that objects do not spontaneously materialize. Empty space does not suddenly generate matter. Conservation laws appear to forbid creation from nothingness. Yet the universe exists, seemingly requiring either an eternal existence or a moment of creation from nothing. Neither option sits comfortably with our intuitions. If the universe has always existed in some form, that raises questions about infinite regress and the nature of causality. If it appeared from nothing, that seems to violate basic physical principles. Quantum mechanics introduces possibilities unavailable in classical physics. At the quantum level, uncertainty principle allows temporary violations of energy conservation. Virtual particles constantly appear and vanish throughout space, borrowing energy from the vacuum for timescales so brief that the uncertainty principle forbids precise measurement of the violation. These quantum fluctuations pervade reality at microscopic scales. Normally, virtual particles annihilate almost instantly, maintaining the vacuum state. However, under certain circumstances, these fluctuations can become real. Near black hole event horizons, as discussed earlier, virtual particles can separate, with one becoming real while the other falls into the black hole. Some cosmological models propose that the universe itself originated as a quantum fluctuation. In this scenario, the vacuum state of some hypothetical quantum field underwent a fluctuation of extraordinary magnitude, triggering the inflationary expansion that became our universe. The probability of such an event may be infinitesimally small, but given infinite time in a pre-existing quantum vacuum, even infinitesimally unlikely events become inevitable. This explanation merely moves the question one step back, however. What created the quantum vacuum? Why does reality possess quantum properties? These questions probe the ultimate foundations of existence. Some physicists argue that the quantum vacuum represents a necessary framework for reality, requiring no external cause. The mathematical structures describing quantum mechanics may be fundamental aspects of existence that cannot be reduced to more basic principles. Others suggest that our universe may be one among many in a vast multiverse, with each universe representing a separate quantum fluctuation with potentially different physical laws. Still others propose that physics beyond our current understanding must exist, perhaps involving quantum gravity or other theories that unite quantum mechanics and general relativity. The question of something from nothing may represent a category error, an attempt to apply causal reasoning beyond its domain of applicability. Causality, as we understand it, operates within spacetime. Events cause subsequent events according to physical laws. But the origin of spacetime itself may not constitute an event within spacetime, and therefore, causal reasoning may not apply. Some physicists compare this to asking what lies north of the North Pole. The question assumes a framework that breaks down at the boundary it tries to probe. The quantum vacuum, while seemingly empty, possesses structure and properties. It contains fields pervading all of space, capable of fluctuating and producing particles. Is this nothing? Philosophers and physicists debate whether the quantum vacuum constitutes true nothingness or whether it represents something, albeit something very different from everyday matter. We cannot conceptually or experimentally access anything more devoid of content than the quantum vacuum. Whether more fundamental nothingness exists, or even could exist, remains an open question, perhaps ultimately unanswerable given the tools available to physics. The twin disciplines. Finally, we arrive at a misconception that is less scientific and more linguistic, but one that causes endless confusion and frustration: the conflation of astronomy and astrology. These two terms sound similar, both derive from Greek words relating to stars, and both involve observing celestial objects. Beyond these superficial similarities, they represent fundamentally different approaches to understanding the cosmos. Astronomy is a natural science, employing the scientific method to study celestial objects and phenomena. Astronomers observe, measure, hypothesize, and test their ideas against observational evidence. They use mathematics, physics, and chemistry to understand how stars form, how galaxies evolve, how planets orbit their suns. The predictions made by astronomy are testable and falsifiable. When astronomers predict a planetary alignment, an eclipse, or the position of a comet, these predictions can be verified through observation. The entire edifice of astronomical knowledge rests on evidence and reasoning, subject to revision when new data requires it. Astrology, by contrast, claims that the positions and movements of celestial objects influence human affairs and personality. It divides people into zodiacal signs based on the sun's apparent position among background stars at their birth, then makes claims about personality traits and future events based on these signs and the positions of planets. These claims do not follow from any physical mechanism. The gravitational influence of Jupiter on a newborn infant is vastly smaller than the gravitational influence of the hospital building or the attending physician. No known force propagates from planets to humans in ways that could shape personality or destiny. Numerous studies have tested astrological claims under controlled conditions. They consistently find no correlation between astrological predictions and actual outcomes beyond what chance would predict. Astrologers given identical birth data produce widely divergent readings. People given horoscopes written for random dates find them no less accurate for themselves than their actual horoscopes. The confusion between these disciplines causes real problems. Students interested in astronomy sometimes encounter confusion when explaining their field to others. Scientific literacy suffers when the distinction blurs. The names themselves contribute to the problem. Astronomy and astrology both come from the Greek aster, meaning star. In ancient times, these disciplines were not clearly separated. Early astronomers often practiced what we would now call astrology, observing celestial objects partly to cast horoscopes and predict earthly events. The divergence occurred gradually as the scientific method developed and as astronomy accumulated evidence about the true nature of celestial objects. Today, they represent completely separate fields with incompatible methodologies and goals. Astronomy seeks to understand the universe through observation and physical law. Astrology makes claims about human affairs based on celestial positions, claims unsupported by evidence or mechanism. The two should not be confused or conflated. This exploration of astronomical misconceptions reveals a broader truth about human understanding. Our intuitions about the universe, forged through everyday experience on Earth's surface, often mislead us when applied to cosmic scales. The universe operates according to principles that seem strange and counterintuitive precisely because they fall outside our evolutionary experience. Gravity never reaching zero, space expanding without expanding into anything, quantum fluctuations creating reality from vacuum. These concepts challenge our basic categories of thought. Yet they represent our best understanding based on observations, mathematics, and experimental evidence. The process of science involves continually refining our models, discarding ideas that fail to match evidence, and embracing new concepts that better explain the cosmos. The misconceptions discussed here represent stepping stones in that process, simplified explanations that served temporary purposes but ultimately proved inadequate. Understanding what we got wrong illuminates the path toward understanding what might be right. The universe continually surprises us, revealing phenomena stranger and more wonderful than fiction could devise. Our journey to understand it requires humility, rigor, and a willingness to abandon cherished notions when evidence demands it. The cosmos we inhabit is far more vast, ancient, and magnificent than our ancestors imagined, and likely far stranger than we currently comprehend. Each corrected misconception brings us closer to glimpsing the true nature of reality.